Okay, so I have unmuted everyone. Okay. So yeah, Saurabh sir will not be joining, I think, okay, because I am the one who is going to take to webinar. So feel free to ask any doubts, okay, in between. So let me share my screen. So can anyone reply that is my screen visible or not?
Right now it's not visible.
Great. Okay, just wait for 1 minute. I am sharing my screen. Okay. I think now is my screen visible?
Yes. It's all black at my end.
No.
I don't know. Yeah, now can see the screen.
We
Okay.
can see slide.
Yes, it is visible.
Okay, okay. Thank you, guys. Thank you.
Yeah,
Thank
it
you
is
so much.
visible now.
Okay, so first we'll try to recall few definitions and few results what we have seen till now, and then we'll try to solve the questions that have been asked in previous years, okay, or maybe in assignments or somewhere it has been asked. We'll try to see how to approach them and how to solve them, and feel free to ask any question in between. Okay, so fine. So what we are going to, so the agenda of today's webinar is going to be, yeah, so agenda is we are going to see problems on this these topics. That is, first is solution of the system of linear equation, and then we'll see one problem on vector space or subspace.
I may be
Your
wrong,
voice
sir.
is breaking up in between.
Yeah, I may be wrong, sir. Not very sure, but guys, please correct me. Have we covered all these topics in the class?
So mostly we have covered till
Not
vector
all.
space. I think.
Yeah.
I'm
to
not sure
vector
about the
space.
subspace, basis and dimension, inner
The
product.
last two are not covered for sure.
Last two are
No,
not covered.
basis and dimension are covered. Only inner products are not covered.
That depend on the professor. I think with Saurabh we have covered till vector space. Please correct me if I'm wrong.
Yes, till vector
Yes,
space
yes.
we have covered. Yeah.
So linear independent and dependent also covered in last class, right?
Yeah,
Yes.
I think linear independent and dependent we covered.
Yes, and we also discuss about basics of basis and dimension. We start
Yeah,
with the
basis and
discussion.
dimension was done, yeah, at the last part of Sunday. Yeah.
Yeah, it
Yes,
was
yes.
just started. I think the detail will be there.
No,
Still
till
there.
basis and dimension sir has covered.
Yeah, that is only it. That last 10-15 minutes. That is all about basis and dimensions.
Yeah.
Okay. Seems Mr. Ankur has left us.
But the good thing is the webinar is recorded. So that's a good thing.
Just, if I don't know anyone facing the same issue or not, but same thing I realized with the last webinar happened with the statistical mathematics. So few things were not covered by the other professor.
I don't know why they're keeping in the weekdays, so even though we are in office.
कल तो भाई बहुत फ्रेश थे। तेरा फोन चल रहा क्या? क्या? फोन चल रहा क्या? फोन आ रहा है, ये तो बात करती है अभी। तुम्हारा कितना? फोन का है क्या?
I'm moving to another professor, guys.
Oh, namaste, Ravi.
Hello. Sorry
Hello,
guys,
hello, Ankur ji.
yeah, I was teaching actually. I did not.
Ankur ji, the student's microphone is on and they are speaking. It's everything is getting recorded. Kindly disable their mic, sir.
Okay. Fine. So I have disabled it. Hello.
Yes, sir, you are clearly audible now.
Okay. Can you just tell me, is my screen visible or not?
No, sir, not yet shared.
No, not yet shared.
I think sir is facing some technical difficulties on sharing his screen.
Yeah.
So,
Guys,
Now visible, sir.
yeah, I was just facing some internet issue. Okay. So I think now it's fine for everyone.
Yes, sir.
Yeah, thank you. So so what I was already taught some slides. So today's agenda of the webinar is we are first going to see some problems on system of linear equation, and then we'll see one problem on vector space, subspace, linear dependence, independence, row space and null space, how to find the row space and null space. And then we'll see one problem on basis and dimension and one problem on inner product spaces. Okay, how we can use inner product spaces to find the distance between two vectors A and B. Those kind of problems we'll see. Okay, so let me first start with what is we call as elementary row transformation. So for example, let's suppose a simple matrix 3 cross 3 matrix. Okay, so there are three ways to do the elementary row transformation. First is either you can interchange any two rows. Okay, so let's suppose we interchange R1 by R2. So you can see here in R2 place it will become R1, and in R1 place it will become R2. So you can do and second one is you can multiply a row by a non-zero constant. Okay, so let's suppose we write k times R3, so it will become k times C1 plus k times C2, k times C3, but R1 and R2 will be unchanged. Similarly, the third one is we can multiply k times row 1 to row 2 or hello, can you please unmute yourself? So let's see. R2 is if we want to do this third row operation. So R2 we are replacing with K times R1 plus R2. So it will become K times A1 plus B1, K times A2 plus B2, K times A3 plus B3. So these are the elementary row operation which we are going to use to convert a matrix in row echelon form or row reduced echelon form. Okay. So next definition is what is echelon form and what is row reduced echelon form. Yeah, reduced row echelon form. So one is row echelon form and one is reduced row echelon form. So one is REF and one is RREF. Okay. So what is the difference between them? And usually we try to find REF only. In special cases only we will try to see what is RREF. Okay. So for any rectangular matrix, when we say that a rectangular matrix is in echelon form, so it has to have three properties. First is all non-zero rows are above any row of all zeros. So the zeros row will be below, and any row which has any non-zero element, it will be above. Okay. So let's suppose this kind of thing. Okay. Sorry. Yeah, here also one.
புரியல.
So second is
அப்படியே நான் நடுவில் 8 மணிக்கு கிளம்பிடுவேன்.
Can you please mute yourself?
Sir, can you please mute everyone?
Yeah.
Yeah, sir. Please mute everyone.
Yeah, but the problem is that this is a problem solving session. Okay. In this session, you should ask the questions in between if you have any doubt. Okay. So that's why I have unmuted everyone. But few people are making noises. So let's see. Please, guys. Okay, it's for everyone. So thank you. So next is each leading entry of a row is in a column to the right of the leading entry of the row above it. Okay. So what does that statement means that let's suppose this has leading entry in this row. Let's suppose 0. So this is your leading entry in this row 0 1 1. So first non-zero entry is your leading entry, and second row is 0 1 0, and third is 0 0 0. And in second one also you have this 1 0 1 0. Okay. So fine. So that means each leading entry of a row in a column to the right of the leading entry of the row above it. Okay. So it should have in the right, not in the left. Okay.
So in this case, sir, it's not a REF, right? Because the below R1 is it should be a little right at the end.
So okay. It should not be like this. It should not be like this. I am giving example 0 0 1 1 0 0 and 0 0. Sorry, 0 1 0. It should not be like this. Okay. Because you see in the second row, the leading entry is in the left of this first row. In first row, the leading entry is in column 3, but in second row, the leading entry is in column 1. Okay, it should be in the right. So your matrix typically should be like this. So it should be, let's suppose this is your leading entry, and then you have some 0 or then some constant A. Then the second, in the second row, the leading entry should be right to this first one. So that means it should be here, and then you can have some A2, and then sorry A2, and then 0 0, and then the third one should be here 1. Okay, it should be like this. And last point is all entries in a column below a leading entry are 0. Okay. So all entries in a column below a leading entry. So let's suppose this is your leading entry in the column 1. So all the entries below this should be 0. But
sir, your voice, sir, sorry to interrupt. Your voice is coming first, and then your marker is moving a little later. There is a gap of 3 seconds. Not sure if it is for me or for rest of the guys.
Okay. Maybe
there is a lag, sir. What I see.
Okay. So the third property, what I was explaining is this all entries in a column below a leading entry should be 0. Okay, so let's suppose this in this matrix. So you in the first column, if you have 1, so all the entries below should be 0. Okay, but not above. So let's suppose in this one, this entry can be non-zero also. This entry can be non-zero, but below this should be 0. Okay, but if you'll go in RREF, then the main difference is that your leading entry in each non-zero row should be 1, and the second is that in that column in which the leading entry is there, the above and below all the elements should be 0. Okay, so RREF will be like this 1. So if this is 1, so below will be also 0. If this is 1, so above and below will be also 0. Okay, and in third one, you can, if you have this 1, so above will be 0. So this is in RREF. But
Why the first element is 0? It can be non-zero as well, right?
No, I am saying if you convert any matrix in RREF, okay, so if you have a leading entry in any column, so let's suppose we have leading entry in column 1, so above and below of those leading entries, all the entries above and below should be 0. So in the below, both the entries should be 0 if it is in RREF. But if it's in just REF, then you can have leading entry other than 1 also. So let's suppose you have leading entry 2 here. So the below element should be 0. And let's suppose you have leading entry 3 in the column 2. So the below entry should be 0, but above entry can be non-zero also. Above entry can be, let's suppose 1. Okay.
I think, sorry to interrupt, sir. I think the fourth point in RRER is the leading entry in each non-zero row is 1. So I think it has to be 1. It cannot be any other number, I think. This is
Where?
what it means. In the
Yeah,
fourth
yeah.
point,
In the
it should be
RREF,
1 for. Yes, sir.
yeah, in RREF, if you're converting, your leading entry has to be 1, but I am explaining what is the difference between REF and RREF. So REF is more like you need less step to do REF, but doing RREF, you need more operations and more steps. So it is numerically very costly to do RREF. So that's why in most of the cases, we just do REF and we go ahead. Okay, because it requires less computing time. Fine. So in RREF,
Sir,
yeah.
I have a question. In since we are doing elementary row operations on on some equations, so
matrix,
how
yeah.
do we matrices linear equations tree? So how do we like see like what number we have to do? It is just by observing, or is there any trial and error basis?
No. See, there is a proper method. Okay. So first you convert anything to matrix. Okay. So let me explain. So let's suppose you have this matrix 1, 2, 3. Let's suppose here you have 4, 5, 6. You have 7, 8, 9. Okay. So let's suppose you have this matrix. So now you want to convert this to REF. Okay. So what you can do, you can first take the operation, first apply the operation. You convert row R2 is nothing but R2 minus 4 times R1. Okay. Second operation you can apply, R3 is nothing but R3 minus 7 times R1. So if you do this one, then your matrix will, first you will get this 1 and the below entries will be 0 by these two operations. Okay.
Okay.
And then what will be this entry? This entry will be minus 3, because 2 times 4 is 8 and 5 minus 8 is minus 3. And similarly 6 minus 12. So this will become minus 6. And what will be this? This will be 8 minus 14. This will be minus 6. and this will be 9 minus 21. 9 minus 21 is 12, minus 12. So now you can see in first column you have leading entry 1, and all the elements below this leading entry is 0. Okay. Now you have to convert this to. Okay. So next operation what you will apply? You will apply this. R3 is nothing but R3 minus 2 times R2. So then you will get what you will get?
1, 2, 3, then 0
1,
minus 3
2,
minus
3,
6, then
0, 0, minus 3, minus 6, and then you'll get 0, 0. Okay. So this is in REF. Why? REF. Because in each column, in this column you have leading into this, and in this column you have leading into this. So all the elements below the leading entry is 0, and all the leading columns is in the right. Okay. So after minus 3 there is no leading column. Okay. Because this is 0. It has to be non-zero. Okay. So this is in REF. All your leading columns is in the right. Okay. But if you want to convert this to RREF, then you have to make this element also 0, 2 and 3 you have to make, 2 and 3 also you have to make. Okay. Fine. So I hope you got it, how to convert it. Okay. You have to see the matrix and then try to make it 0. Okay.
when the third row is
Sir,
0, what it tells us, like, is there is no solution? Suppose the variables are x, y, z, so z has no solution.
Wait. That comes later. Okay. We'll discuss.
Okay, sir.
Yeah.
sir, in RREF, the output will always be identity matrix.
No, you can't say it will always be identity matrix. It can also be like this now. It can also be like this. This becomes 0, 0, 0. Third row becomes 0, 0, 0. Second row becomes
Okay.
0, 1, 0. And first row becomes 1, 0, 0. So this is not identity matrix. It's like
But
identity matrix.
but the elements which will be left will be diagonal and will be one only.
Yeah. And all the if any column has leading entry, it has to be 1, and all the entries above and below has to be 0. Okay. Fine. So
Sir,
next,
by any chance, can you show us two matrices side by side? One should be REF and one should be REF. Where final converted one, that will give clear picture. Little bit kind of confused. I'm not sure.
yeah. So in this one only, okay. So this is an REF form. This one you can see 1, 2, 3, 0, minus 3, minus 6, 0, 0, 0. This is in REF form. But if you want to if you want to convert in RREF, then you have to again apply one more operation. That is R1. We are going to change R1 by R1 minus. We want to make this element as a 0. Okay. So what we can do, R1 plus 2 by 2 by 3. 1 by 3. Yeah. 1 by 3 times R2. So if we replace R1 by R1 plus 1 by 3 times R2, so we'll get 1, 0, 0. Here we'll get minus 3, and here we'll get 0.
We should multiply with 2 by R3, right, sir? 2 by 3 R2, I believe so. Not
R1,
1 by R1
yeah,
plus it should be 2 by 3 R2.
Yeah, you're right. 2 by 3 R2. Yeah, you're right.
Okay.
So this element will become 0. Okay. And what about this one? So 6, 12 by 3, 4. So this will become 7. Okay. Still it is not in RREF because your leading entry in the column should be always 1. Okay. So now we will apply R2 by minus 1 by 3 R2. Okay. So then this will become, this will come in form of 1 0 7 0 1, and this will become minus 2 0 0 0. So you can see you have 2 leading entries, one this, one this, and all the elements above and below to this leading entry is 0. Okay, and all the leading entries are 1. So now you can say this is in RRE. And in third column you can see you don't have any leading entry because it is 0. Okay.
So rank is 2 here, right?
Huh?
Rank is 2.
Yeah, rank is 2. Yeah. So next, yeah, we'll see next thing. So the rank of a matrix in its echelon form or REF form is equal to number of non-zero rows. Okay. So how many non-zero rows you have? That is the rank. Okay. So what about this matrix? Can anybody tell what is the rank of this matrix? First one. And what is
4.
4.
4.
Yeah.
4.
4.
Second is 3.
Second one is 3.
Yeah. But these matrices are already converted in REF form. Okay. This one is in RREF form. You can see.
First one is in REF and second one is RREF, right? Am I correct?
No. First one is see. In first one also.
No one is in RREF.
Both are in RREF.
REF only.
Only REF, right?
Both the matter.
Both are RRES, right?
RREF, because you can see all the leading elements are 1. Okay. And all the elements above and below to leading entry is also 0.
No, but the third column is not right. Third column.
Where?
So third column
the first
5700 in the first matrix, third column.
Yeah, third. But there is no leading. There is no leading entry in the third column.
The leading entry is 1. So third column is not a pivot column.
Yeah.
Fourth column is the pivot column. So your fourth will be considered as the that one will be considered as leading.
Yeah. So you can see this both the matrices are in RREF form. Okay. Because in second also you have 1, all the entries above and below is 0. In this one also you have all the entries above and below 0, and here also you have all the entries above. So both are in RREF form.
So it means if we are able to get any one column with a leading 1 and all above and below are zeros, then it is already in RREF, right?
Yeah.
And leading entry should be always 1, and it should be right side. Next entry should be just right side. Be it a column a skip or it's the same column. Sorry, next column. Is that correct?
Yes. It has the
Thank you
next
so
pivot
much.
right, not in left. Okay. I hope it's clear. And next is system of linear equation. So here we are considering a system of M linear equation.
So what?
Yeah. Yeah. Let me finish this. Okay. Then you can ask. Okay. So consider a system of M linear equation in N unknowns. So you can see we have M equations, and a number of unknowns is x1 to xn, and we have number of equations a11 to am1. Okay. So this is M rows and columns. So a M cross n matrix, that is called rectangular matrix. Okay. If M equals n, then we call this as. So we'll see if all this B1 to BM, okay, all are 0, then the system is said to be homogeneous. Otherwise, if one of them is non-zero, then we say that system is non-homogeneous. Okay. The set of values x1 to xn which satisfy all the equations simultaneously is called the solution of the system of equation. And a system of linear equation is said to be consistent if it possesses a solution, otherwise it is said to be inconsistent. Okay. So this system, we can write this system as A x comma b. Okay, so if B is 0 matrix, then we call this as homogeneous system. If B is non-zero column vector or matrix column, yeah, usually n rows one column matrix is called column vector. Okay, so if B is non-zero, then we say this system is non-homogeneous, and a system if has any solution like one solution also, then we'll call system as consistent. Otherwise, we call, if it don't have any solution, like no solution, then we'll call system as inconsistent. But you can see if your system is like AX equals 0, where 0 is 0 column vector. Okay, this 0 is 0 column vector. Then you always have a solution which is 0, because A times 0 matrix is nothing but 0 matrix. Okay,
So
this
what is meant by homogeneous system here? Like how come the systems come here in this class? Is the meaning of?
homogeneous means your left hand, right hand side, all the entries should be 0. Okay, so if all this B1 and B1, B2 and BM all are simultaneously 0, then we call this system as homogeneous system. Okay, fine. So if a system is homogeneous, it will always be consistent. Okay, because it will always have solution as 0 solution. Okay, so it can't be inconsistent. And if system is consistent, then there are two ways. Either system can has infinitely many solution, or system can have unique solution. Okay, and that we'll see later. But if system is inconsistent, that means system don't have any solution. Okay,
Zero solution means no solution, right, sir?
no,
And
no,
then
no,
when you say
no. Zero solution means the zero vector is a solution. Okay, so this, let's, in this one, AX equals 0, where 0 is 0 matrix. 0 matrix means all the columns are 0. Okay, so in this AX equals 0, this will always be solution, because A times 0, 0, 0 is 0. So let's suppose I am explaining this one. Okay, so let's suppose you have x plus y equals 0, and you have 2x plus 3y equals. So you can see 0, 0 is always the solution of the system. Okay, but if I change this, make this system like this, x plus y is nothing but 1, and 2x plus 2y is nothing but 1. What about this? This system has how many solutions?
Zero solution.
No, zero solution. No solution.
No solution.
Yeah,
It has no solution.
Yeah, because simultaneously any x and y will not satisfy these two equations. So this system is inconsistent. Inconsistent means it will have no solution. Okay, fine. So we'll see problem based on this system of linear equation. Okay, first we'll see what is vector space. I think you guys already know. So let R denote this set of real numbers, and V be a non-empty set for every order pair on which two operations, one is vector addition and scalar multiplication, are defined. If these listed axioms for every U, V, and W in V, and scalars C and D in field F, okay, which is real number, then V is called a vector space over the field. So how many properties it has to satisfy? It has to satisfy all these properties. First is it should be closed under addition, it should be commutative under addition, and it satisfies associative property. It should also have zero vector, that is called as additive identity. It should also have additive